I don't think I can tell any of you anything new. There's a lot of expertise here. So what I'll talk about mostly is development of tephra. Okay, here I am, ready to go. The discipline of tephrochronology is quite young, relatively young, as we heard. Prior to the late 1930s, tephra was often regarded as a curiosity in stratigraphic sections. It was used by some geologists for local correlation, and in the late 30s and 40s, Sigurdur Thorarsson did a systematic study of tephra, as we heard, and used it to correlate tephra. He used primarily stratigraphic and physical characteristics of tephra and their stratigraphic sequence, and and he introduced the terms tephra and tephrochronology. In the late 50s and into the 60s, Ray Wilcox of the USGS began to apply petrographic characteristics to identification of tephra. I'm kind of biased towards Western North American tephrochronology because that's what I worked in all my life, but just keep in mind that a lot of these developments, parallel developments, were occurring in New Zealand and in Europe and Africa and Asia. So he used minerals that were present in tephra layers and their physical properties, their optical properties, indices of refraction of the minerals in the glass to characterize tephra, and made some important advances in that respect. In the late 1950s and through the 1960s, there was a burst of development of new analytical techniques, and this continued on through the 1990s and to the present time. Development of X-ray fluorescence, electron microprobe analysis, INAA, ICP-MS, progressively through time. So the development of these new techniques gave great new potential to tephrochronology and a whole new basket of toys to play with and to apply to the study of tephra. So tephrochronology combined with the development of new chronostratigraphic techniques such as isotope dating, magnetostratigraphy, marine oxygen isotope stratigraphy, all of these things together is now applied widely and often effectively to a wide variety of scientific studies. And all of these studies are interrelated to some extent and at one end or another, at one point or another, and they're most effective when they're used in combination. A recent review article by David Lowe sort of describes the spectrum of things that are being done in tephrochronology and in chronostratigraphy in general. This is sort of a summary diagram of quaternary geochronologic methods and chronostratigraphy, and it involves many disciplines. And I think that no single individual can really comprehend it all, be on top of it all. So it's obviously a tephrochronology in particular is something that relies on cooperation among various specialists. And as John pointed out, it's a two-way street. Tephrochronologists get information from other disciplines and vice versa. Now, concurrently with the development of these new techniques and methodologies, the number of scientists and technicians that are doing this stuff has exploded. So rather than a handful back in the 1940s and the 1950s, there's probably several hundred people doing this, maybe into the thousands. I've tried to figure out how many, but I guess we could look at the INTAV membership. Anybody know how many people there are who belong to the INTAV Tephra group? Anyhow, So a coordinated effort to share data and to catalog it, particularly with regard to Tephra chronology, can make our research efforts much more effective. And some such of these efforts have been going on in an informal, ad hoc manner for quite a while. Sharing of comparing data, sharing standards, sharing information on instrumentation, and establishing conversion factors between databases. So all of these efforts have been going on already in an informal manner, but we can make our research efforts much more effective by a more organized system of arranging and comparing our data and sharing it. And some of these are, as we'll hear, are already going on. Now, Tephra is widely distributed during and after eruption. And when Tephra falls, it respects no political or geographic boundaries. Eruptions may be of subcontinental size, continental size, intercontinental, as we've heard, and maybe even hemispheric, global in extent. I guess we'll hear about the Toba later on. But even a small eruption like Mount St Helens in 1980 was at least a hemispheric event, if not a global event, because as you can see, the occlusion of atmosphere a month or two after the eruption was quite significant and global. So it means that fine material from this eruption was spreading globally and migrating towards the pole. And there is some indication that maybe even further in the southern hemisphere there was some occlusion of the atmosphere a few months after that. So if a small eruption can do this, as we can see from modern observations, then some of these mega eruptions obviously were global events as well. And in recent years we've had reports of pole-to-pole, or at least just Greenland to Antarctica correlations, and this is very exciting. This indicates that this can be a tremendous tool for global correlation of various things. There are a few comments I want to make about this later on in my talk. Now, mostly, since I can't tell you anything new, I want to tell you something about the development of Tephra, something old. And this is, I got out of the service in 1962, and mostly to get out, I applied to UC Berkeley to study geology there. And I could get out a couple months earlier out of the service if I got accepted to a grad school. So that's what I did, because the Corps of Engineers was not a stimulating environment, and I wanted to get out of there as soon as I could. So these are some of my colleagues at UC Berkeley on a field trip in 1962. And you probably recognize some of them. I'm at the extreme right there, eating an apple, tasting the apple of knowledge, I guess, at Badwater in Death Valley. Now, at first I thought I'd go into economic geology, but soon I got sort of seduced away into Quaternary geology, and I thought I'd do a history of San Francisco Bay. Is there a pointer here? Does this work? Oh, sorry. I'm a techno dad, as you can see. I just took the audio recorder out. And this works.
Here's the button. Here.
There we go.
Tiny one.
All right. Okay. So I thought I'd do something about the history of the bay. You know, look at some of the bridge crossings. There are cores in the bay along the lines of the bridge crossings. There's a proposed southern crossing, so there's some subsurface information. And then there were all these patches of presumably tectonically and otherwise isolated areas that were above the bay that are in this color, sort of a beige colored. These were all lumped under QP. And I thought these might give some, information about the history of the bay and the tectonics of it and all that. So I started looking at these, and then I realized that the reason they were put into a QP category was that there was no age control for these things at all. So there was a little bit of a few vertebrate fossils, some marine fossils in the marine beds, but by and large there was very little age information. So I came kind of to a standstill, but here and there were these nice thick white beds, which turned out to be tephra, so I started working with these. I thought maybe I could get some age control on these things. So at that time, we got at Berkeley, several new instruments. One was an X-ray fluorescence spectrometer. We also got, a few years before I came, they set up a potassium argon lab, one of the first in the country, and then they also got a microprobe. So there are all these new analytical capabilities that I could work with. So I thought, wow, maybe we can try this. And some other people had tried this already. Jack and Carmichael and another student who came ahead of me experimented with this. So the thing that we did was what I did was to first of all, just take this X-ray fluorescence machine and experiment with the tephra. See what kind of components there were in it. See what seemed to give the best results for correlation purposes. And I'd run rapid scans through a 2 theta interval. This is a background from the tungsten tube, and these are little peaks for minor elements: rubidium, strontium, yttrium, and zirconium. And then I just measured the net peak intensities and sum them up and plot them on a ternary diagram, like, for instance, rubidium, strontium, and zirconium. And the first unit I tried this was a well-exposed unit in the Bay Area, the Luller Tuff. You could follow it across country for quite a ways. Here it is in red. This is the type locality of the Luller Tuff in Luller Canyon. You can follow it here for about 10 kilometers or more. So you could sample it along strike, and you could sample it vertically. And actually, this unit is airflow at the bottom and has an ash flow on top. So I could look at both. And so I did that, and not necessarily any systematic way. And the initial scans on these things were a little scattered. Strontium substitute for calcium, so it proxies for that. So it tells us something about what calcium is doing as well. Zirconium proxies for nothing else except zirconium and hafnium, which usually concentrates in zircons. And the rubidium follows the alkalis in geologic systems, so it proxies for alkali feldspars. So this told me what might give best results. Obviously, analyzing a whole tephra logically didn't make sense. If you're looking at a tephra that's falling out close to source and then maybe 100 kilometers away or 1,000 kilometers away, there's going to be changes in the bulk chemistry because things are settling out, heavier crystals and so on. So I looked at feldspars, and the feldspars, concentrated in this towards the strontium end, in other words, calcium, and the sediments above and below this tuff scattered here, and the caliche was over here towards the strontium end, meaning that there's mobile strontium and calcium in the section. All of these things could affect, could be contaminations. Magnetic separates, for instance, the ferromagnesian minerals tended to go here. The non-magnetic separates were concentrated towards zirconium. That meant there was a lot of zircon in the section. And then when I started separating these things gravimetrically using bromoform, I found out that I had a lot of bromine error error introduced into the rubidium concentration by not drying the samples out well enough. So there was actually an error introduced by the process of an artifact introduced by working with a tephra, and I've worried about this. And none of this was, you know, a straight logical deduction going from point A to point B. You know, it was more like a random walk. Let's see what this does. Let's see if this works and that works, and always an anxiety that I'm doing something wrong and maybe I should be studying music or something else. Nevertheless, some things emerged slowly out of all this, that the scatter was reduced by, for example, treating the sample with 10% hydrochloric acid for a while, and that probably removed the carbonate that was secondary carbonate in the soil. And then after separating this material, just separating out the glass, I got a nice tight cluster. So I said, yeah, glass looks like a good thing to work with. And then I could follow this tuff all over the Bay Area and identify it by this composition. And I went on to doing the actual parts per million and other oxides and elements. Then I went to the probe, and this was a disastrous detour because when I looked at the pyroxenes and the amphiboles, they were all zoned, so they gave very wide distributions. And so I also analyzed some glass, but I decided that the probe wasn't a very good technique to use at that point. This was around 60, somewhere between 65, 67. But Jonathan Davis at the Desert Research Institute, he and I started cooperating, exchanging data, and he said, probe is really good. You know, you really should stick with it because it's a very quick, easy technique, and it works on glass. And then if you don't really nail it, if there's some question about, you know, whether it works or not, by distinguishing between several units that are similar in composition, you can go ahead and, you know, do something else. Or else you can use what he called homotaxial succession, where you have a sequence of beds going up, you know, XZYB here and XZYB there. The probability that those two are formed by chance is very low, so they're probably the same units. So I was able to, the red dots here show the distribution of the Lawler tuff in the Bay Area, and the other colored dots are tephra layers above it. And we're able to tie these outlying areas into the source area, which is the Sonoma volcanic field. And actually, that was not such a great discovery because the gradients on these ash flows increased in this direction, so we kind of knew that this was the source. But something else that came out of this was that a lot of these localities were offset by left lateral strike slip displacement along the San Andreas fault zone in the east part here. So we were able to tie the Lawler tuff into the section and eventually worked out the chronology of the Sonoma volcanics. Now, statistics can be a bore, but it's like dirty dishes, you got to do them. So, you know, you can have a very nice tight cluster for your factors and be happy and go home, but you got to show that that particular tight cluster is significantly different from that particular cluster. In other words, you got to show that the internal variability of the units that you're working with is unique, is different, and doesn't overlap with something else. At least you have to have several dependable factors by which you can distinguish these things. And even with electron microprobe analysis, we could distinguish the Lawler from the Huichica here, which closely overlies and is very similar tuff and came from the same volcanic field. And this is neutron activation analysis on both of those units. The Lawler tuff is in blue and the Huichica in red. And you can see they track very, very closely for all elements. And you could say, well, how can you tell the difference between these two things? Well, the rare earths, lutetium in particular, the difference in replication, the standard deviations between this and this are separated by 10 standard deviations. So you can be, fairly assured that they're different populations. And so we were able to take this tephra layer and correlate it among a number of sites in the Bay Area and extend the correlations out to the rest of California, getting a distribution here for the Lolar tuff, going on into Nevada and all the way from north to south here. Buzzards, in Buzzards Peak, it's become an important marker for dating the inception of Colorado drainage down through cutting down through the Bouse Formation. It indicates, or at least suggests, that the drainage had to be formed sometime after 4.8 million years, the age of this tuff. And this is the Huichica tuff that overlies the Lolar, and this is the tuff of Napa. So we're sort of building up a stratigraphy here. Our work can be described in two ways, which are actually complementary, and as two different kinds of studies. One is a, how am I doing on time, by the way?
A little bit over.
Okay. Yeah, I think I started about 10 minutes later.
Yeah.
Okay. All right. So one activity is a site study where you actually maybe coring or looking at a section where you have a number of tephra units in a section. This is a particularly nice one where you have multiple units at Confidence Hills in Death Valley, which is right here. This is the distribution of the tuff of Blind Spring Valley. These are a number of tuffs that are right here. And we also have magnetostratigraphy from another study, and we have the stratigraphy from yet another study, and then there's our study in cooperation with Benny Troxel initially, and then our later study. So it was a cooperative effort, but it was basically a site study. But these studies also tie into much broader regional studies, because here we have the Huckleberry Ridge ash bed, which is from a different source. The tufts of Blind Spring Valley are out of here, and that's their known distribution. And the Huckleberry Ridge ash is out of here, as you know, out of Yellowstone, and this is its current distribution. It's actually larger by now, and it'll eventually be global, I presume, based on what we've heard and what we've learned and what we'll probably hear in this meeting. Bishop Tuff out of Long Valley Caldera here, 774,000. You've probably seen some of these figures already in my previous talks. Lava Creek ash bed out of here, out of Yellowstone again. Some of these are showing up in deep sea cores. So this is Lava Creek in Lake Tecopa. It's about 3 meters thick. This is a Western-style cryptotephra. Here's a close-up of it. It's most of it. It's 3 meters is already worked. It's part of the Amargosa drainage was blanketed with this ash, and the terminus was Lake Tecopa. And when the rains came, they carried all that stuff down into Lake Tecopa. And tephra is light. It's the first thing that's going to be carried. It covers all the surface, so you're going to get a nice, pure, reworked tephra. Very beautiful angular shards. And now we can develop these monster fingerprints based on not one or two or three, but many different analytical techniques. This is EMA, INAA, and this is ICP-MS for the Lava Creek B. And we have lots of factors to play with. I could have added X-ray fluorescence to this, but ran out of space. So this is what some of these tephra layers look like. If you're wondering about the histograms, they're actually ratios to a USGS standard, so you can show everything on one diagram. if you have lutetium at 0.5 parts per million and silica at, 78%, you can't show them on the same diagram. So this is why they look like this. And you see very, very strong family resemblances in the tephra layers that erupted from particular provinces, like the Huckleberry Ridge and the Lava Creek Beat track very well together here for all elements and the rare earths as well in particular. So this kind of a pattern, very enriched in rare earths, is an indication that the magma is being formed in old cratonic batholiths that have been melted and remelted repeatedly, multi-cycle things where the incompatible elements have accumulated. Whereas things like, let's say, Mount St Helens and Mount Mazama, which are shown here by orange and yellow, they also track pretty well, but they're much more enriched in the compatible elements and depleted in the incompatible elements. So the tectonics of the setting tells you something about the composition. The cascade range is produced by volcanism from a subduction regime, and material is poorly evolved. So there's a very close correlation between the composition and the tectonic setting, the plate tectonic setting. The Bishop is probably out of a younger batholithic system, Mesozoic batholiths, the Sierra Nevada batholiths, and that's depleted in the rare earths. And the Rockland is actually transitional. The Rockland ash came out of the southern Cascades, and it's probably partly coming out of Sierran batholith and partly coming out of the part of the subduction trench regime. So the terminal aim, the goal of all this activity is to develop a spatial and temporal four-dimensional framework that can be used for other scientific investigations. And this is just sort of an illustration of that. These are late Pleistocene 4 late Quaternary units in the western U.S. This distribution here is the bent pumice that was mentioned before. Bent pumice was erupted from here and went east, and most units go in other directions. A lot of them tend to go north, east, or south, but this one went west. Why that is, we don't know. One possibility is that it came out during a glacial period when there was a permanent cordilleran ice sheet and a anticyclone, a high-pressure area that at the south end would make the winds go in this direction. Here's some middle Quaternary units, some of which I mentioned before. And we've been able to correlate these to deep-sea cores. Here's the Lolita ash bed is actually the bent pumice. The reason it's called Lolita is that we first found in Humboldt County, near the town of Lolita, Huckleberry Ridge, and the Kilgore Tuff. This is out of the high sea volcanic field, which is part of that Yellowstone trend. So this is a interesting, perhaps odd-seeming factor that we're finding Yellowstone Tephras out there in the Pacific Ocean. How did they get there? Did they go all the way around and fall down there? I don't think so. I think the reason we're finding them is that these are mega eruptions which go through the tropopause into the stratosphere. In the stratosphere, there are counterwinds that can take tephra in the opposite direction. I think I'm going to end it here. I was going to tell you about some of our African work, but I think I'm running out of time, so for the sake of keeping this on track, I'll end it here.